Welcome, everybody. Welcome into this guest speaker lecture. For those who are in block 4, this is the final week of the course. And so this will be our final guest speaker lecture for this cohort, though there will be many. Today, we are being joined by Don, who's the co-founder and CTO of Mem. Mem is a Web3 social company building technology to enable users to own their own data and transfer it around the internet. Prior to Mem, Don worked as a machine learning engineer. He graduated from Berkeley and he's got a master's in mathematics from Rutgers. Don, thanks for joining us today. We're super happy to have you, and we are greatly anticipating this talk on ZK stuff. So please, the floor is all yours.
Yeah, we're going to be talking about ZK proofs today. Rather than going kind of headfirst into a specific zero-knowledge proof system, we're going to do a tour of zero-knowledge primitives and kind of foundational stuff and what it actually means for something to be zero-knowledge and the different properties that these systems have, interactive versus non-interactive, and what those actually mean. So ZK proofs. One thing to clarify is what we mean by knowledge, right? Before we even get to zero knowledge. So there's a lot of buzzwords floating around: ZK rollups, snarks, starks, plonks, marlin, shark, snort. One of those is made up. So zero knowledge systems are cutting edge stuff. A lot of development going on in Web3, but we really should understand what we mean by knowledge when we're talking about that. So if you're familiar with computational complexity theory, the field's information theory, and information theory is all about being able to quantify through bits and complexity the size and the communication of messages and data. But when we're talking about knowledge, we're talking about computational difficulty usually, right? When people are talking about zero knowledge, they're saying that basically you can demonstrate something without showing how you got that answer, or giving the person that you're showing the information the ability to get the answer themselves. So you can think of knowledge like skills, and information is just like facts about the world. Everyone going through this course, right? Everyone in this cohort is acquiring knowledge by synthesizing and organizing information that's presented to you. And the way you're organizing that is, you can think of it as computation. So knowledge, again, is about computation, right? To move on to the next slide, Nick. So here's a concrete example about this ice cream cone. Could just be that the temperature is negative 15 degrees Celsius. So that's just a fact about that object. And you can get that from some thermometer, right? You could do the reading yourself, or Jack could also do the reading and just tell you the temperature, right? Just basically anyone who has a thermometer can perform the measurement. But if you're the ice cream maker or you're the ice cream shop owner, and this is your new flavor of the month, you're the only one who knows the recipe of the ice cream. And there's no, simple measurement that anyone could take of a scoop of the ice cream to figure out the ingredients and the sequence of operations that you use with those ingredients in order to actually make the ice cream. So sure, you could go crazy, and maybe if you have some chemical engineering background, you could say, I could do gas chromatography or something, figure out the chemical composition of ice cream. And then from there, I can do some approximation and figure out, based off of some analysis of existing ice cream recipes, so a dictionary attack, and then figure out what ingredients there are. But you still wouldn't, what was the way that the ice cream was churned? For how long was it churned after that? Like, you don't know the sequence of operations that went into it. The only way to get that would be to actually have a discussion with the ice cream maker and have him tell you the recipe. But the ice cream maker can, show you that the ice cream is there after he makes it, and you can taste it. And so you can also then derive some of your own knowledge from that, but that's a kind of separate issue. I know that's like a philosophical kind of discussion, but hopefully that clarifies kind of the distinction between information and knowledge a little bit more intuitively when we start talking about conditional versus unconditional security relative to a certain computational model. So let's go through a kind of simple example of a ZK proof. Seeing the example with Baba, where someone knows a secret. So this is a similar sort of setup. So let's say there's a gym and there's a tall wall separating two red circles in the gym. So the wall's like 2-3 feet, and there's no way to get from the red circle to the blue circle without stepping over that wall. And there's a 150-pound kettlebell. And I want to prove to you that I can move the kettlebell from the blue circle to the red circle. The obvious way to do it would be I just go pick up the kettlebell, walk, step over the wall, and place it on the red circle. And you just see me do that. So you have seen me lift at the kettlebell and you know that I can do it. But what if anytime I lift something over 100 pounds, I just make the most awkward face and I'm really embarrassed about it. And I don't want you to see me make that face when I lift this kettlebell up. So instead, you're going to leave the room and I'm going to move the kettlebell. And then you're going to come back in and you'll see that the kettlebell is on the red circle, right? So that shows that the kettlebell moved, but how can I prove that I'm the one that moved it if you didn't see me move the kettlebell? So one way to do it would be if I had some chalk, I could leave a handprint on the kettlebell when I lifted it. And maybe we designate some spot where you go look. And then you can come in and not just see that the kettlebell moved, but check my palm print, match it against my actual palm and see that it matches. Okay, so now you can have some sort of signature that I've actually performed this action. But still, someone else could have come in while you're out of the room, moved it, and I just put my hand on the kettlebell after the fact. So being engineers, we come up with a technical solution. So we create a mechanical device that can hoist up this kettlebell and we'll randomly drop it onto either the red or the blue circle. It'll do this when both of us are outside of the room. And now, before I go into the room, you call out red or blue. Now, when I enter the gym, either the kettlebell is going to be on the red or blue circle. So let's say you called out red. If the kettlebell is on the blue circle, it's the same setup as before, right? I have to go pick up the kettlebell and walk over the wall and put it back in the red circle. If instead you call that red, I could just go over and leave my palm print on the kettlebell. In both cases, you'd come in and check and see that the kettlebell's in the colored circle that you called out and that my palm print's on it. So in this setup, there's basically like a 50-50 chance that I could have gotten lucky and I didn't actually have to lift the kettlebell. So how can we use this to actually prove that I'm able to lift the kettlebell? We can repeat this experiment, right? Let's say the mechanical device we build can also grab the kettlebell and reload, and then it's ready to randomly drop it on one of the circles again. So if the probability that I just got lucky is 50% if we do it once, what's the probability that I got lucky both times if we do it twice? So it's a simple probability problem. It's 50% the first time, they're independent events. So 50% the second time. So overall, right, it's just the product of the two probabilities, 25%. So if you have some probability threshold, let's say you want to be certain that 99%, you can just repeat this experiment the required number of times, right? You just do some algebra to figure out how many times you need to perform the experiment. And then once you see all those correct observations, then you are certain up to that threshold that I actually can lift the kettlebell. If you ever come in and see that is in the wrong spot, then for sure that I can't. So it's an asymmetric relationship, right? The moment you one mistake, for sure it's wrong, but you need to see multiple pieces of evidence in order to reach whatever threshold that you've set. Any questions on that? I guess this would be a good time to pause before going into kind of like the theoretical definition of zero knowledge.
So you're not establishing, you don't know that it's correct. You just have like higher confidence that it's correct based on the threshold.
Yeah, so that's one of the tricky things when we're talking about zero knowledge proofs, right? They're actually a class of proof called probabilistically checkable proofs, which are, as you just pointed out, they're different. It's a different sense of proof from a classical deterministic proof, right? If you took like a theoretical CS class in college or like a math class, whenever you're doing proofs in there, it's deterministic. It has to be true. Here, this is an evidence-based, so you use probability, right? It's almost like a Bayesian reasoning type of thing.
And do you know what the industry standard is for like that threshold of confidence of probability?
So based off of the optimizations of some of these schemes, you can essentially get like numerically negligible, like it's based off of the precision of your machine, it's actually 0 or close to it. But besides those like numerical optimizations that's asking about what's the p-value I should use when you're reading like an interest stats book. Whenever they show the examples, they just use 0.05 just because of historical reasons, but you're actually supposed to set it based off of the cost associated with making the error. It's like a statistical thing where it's like, what's the sigma you need? What's the level of fidelity you need on it? But if you're running those numerical optimizations, it may be a moot point.
Do you have any examples of an actual number? Because I know they use approximations to generate primes for RSA. I forget the algorithm, it starts with an S. But I think they do that. I think I remember reading 80 times.
Not off the top of my head, but when you get to the goal there is to have an optimization where you don't have to perform as many of those iterations. Or if you do have to perform those iterations, each of those operations is really cheap. So that comes down to proof size parameters and things like that. Any other questions? That was like a concrete example of a zero knowledge proof and mechanics behind those just to get some intuition down. So this is the formal definition of what perfect zero knowledge is. It's a lot of abstract nonsense mathematical symbols here, but it's strictly and formally defining what we were just talking about. Going through each of the symbols here, right? The first thing we have is some language L, right? If you're familiar with computational complexity theory, a language is some set of strings with a structure that you can compute on, right? So there's representation for your data and your functions. So X is going to be some data string in this language. And then the Z string comes from some arbitrary length binary set, right? So that's what the notation with the bracket 0, 1 with the star means. It's a array which could be any length, but is just a binary array. And then we have 3 Turing machines, right? P, V, and S. So P is the prover. So that would be me in the previous scenario where I'm trying to prove that I can lift the kettlebell. V is a verifier. So that would be you, the person who wants to check that I can actually move the kettlebell. And S is a simulator. And this is a mathematical construct to demonstrate the zero knowledge transfer between the prover and the verifier. The view function is essentially a way to describe the interaction history between the prover and the verifier as recorded by the viewer. So that's the subscript V hat there, right? So that's a specific instance of the verifier. And then Z is an auxiliary string, right? So as I said, it could be an arbitrary finite length binary string, but it is intended to represent the prior knowledge of the verifier. Since it's an iterative game, essentially, that we're playing, you send me a challenge. So we both step out of the gym, you call out red. That's the challenge. I have to go in and then I have to demonstrate that I can respond to the challenge appropriately. So if there's any way that you could learn some partial information about whether I was actually lifting the kettlebell each time I went in. So let's say I was starting to break a sweat and that was some good evidence for you. So then you're actually getting some knowledge about my ability to lift the kettlebell. And since it's iterative, you can build up this history. And if a little bit of information is leaking each time, a little bit adds up over time. And that's what this Z string is supposed to represent. So those are all the parts in the expression. So essentially what this statement is saying is that perfect zero knowledge is formally defined as given any piece of data in the language, so given any X in L, even if the viewer is able to record anything they want through this interaction game, which is represented by Z. The recorded history that the verifier V would get from the interaction between the prover, who just has the data string, and the verifier, who is trying to learn the data string and has a record of their interaction history, would be the same as a simulator who just actually had access to the private data and who also was trying to learn X, but had the same access to Z. All right, let me try to make this more intuitive. So every time I was proving that I could lift the kettlebell, I was demonstrating something that could be interpreted as I was lifting the kettlebell. It still wasn't 100%. That's why it's a probability. Let's say I had a machine and I knew the sequence of colors you were going to call out beforehand. Then the results that you would see by interacting with me would still be the same as if I actually could lift the kettlebell, because I can still show you the correct response without actually having the knowledge behind it. So that's what the simulator is trying to represent there. So I know it's a little abstract, but that's essentially the way that you would show the lack of knowledge transfer computation.
A question on that. This is always
Yeah.
the hardest freaking part to understand.
Yeah.
And I've never understood it every time I've read it. And I feel like it all centers on the simulator. So question about the simulator is the point that the simulator is all seeing Turing machine, and even with it being all seeing, because it only has the information available to it through the proof, it still can't find what? Is it Z? I feel like it's not Z, but
It's X.
what is it
Yeah.
that they can't find? X.
So
Yeah.
the way it works in the way it's intended, right? If I actually have the knowledge and I'm trying to prove that demonstrate the knowledge to you without showing you that, we have to perform it sequentially, right? It's this interactive game where you send me one challenge, I perform the response, or I generate the response, and then you send the next challenge, and we keep doing that until the threshold is reached. The simulator has an oracle property in the sense that it knows the full sequence of what challenges you're going to send before. And because it knows the full sequence of challenges using some arbitrary function. So the other thing that's important to note, which I failed to mention about the simulator, is it has unbounded computational power, right? So it's an unbounded Turing machine, right? So you can basically think of it as it can compute any function and it has nothing better to do, so it'll eventually get there. So the idea is that because it has those resources and it knows beforehand what sequence you're going to do, it can use some arbitrary other function to generate responses that would be valid for those challenges, but that function would have nothing to do with the actual underlying knowledge represented by the function that I know.
You as the viewer or you as the prover?
So the simulator doesn't know the secret as the prover, no, but it
Yeah,
can still
doesn't know
generate
X.
all the same right responses. One way to think about it is if I give you some set of points on the plane, I give you like 20 different points on the plane, and I say, give me a polynomial that goes through. You can find a polynomial that goes through that. It won't be the specific polynomial I have that goes through those 20 points, though.
So the simulator can find one of those that satisfies, and the viewer can too. But the point is that they both find a solution that is the solution. Yeah, actually, I feel like we could take up a lot of time talking about this.
I think this should help clarify it. So you got to think of it from the perspective of the viewer and what knowledge the viewer is gaining over the sequence of interactions. Like we did 10 tests. Now, what have I learned so far? Does that tell me anything that I know beforehand to inform test 11, right? Am I more sure that you're actually going to be able to do blue on 11, or is it still 50-50? So the simulator is able to show all the right answers, right? The same that an actual prover who knows that would, right? But the simulator is using some random function that just happens to fit all of your challenges. So from your perspective, you can't tell whether the prover is actually a simulator or not. That's why it's zero knowledge. Because from the verifier's perspective, the prover, even though it's the same probability threshold, the behavior is the same as a simulator who just knows what challenges they're going to say and is lying to them just to fit it.
Yeah, it's not your fault. I feel like I still don't get it. My follow-up question, how useful is this for day-to-day working with proofs? Because I know that this was how it was originally constructed in the 80s. But oftentimes when I hear folks talk like a little bit higher level, they never mention a simulator. I guess I'm saying, are simulators useful if you're not trying to prove a system mathematically it has some security properties?
Yeah, they're mostly used for the security properties. It's basically, the idea is like the simulator represents like a perfect liar. And from the verifier's perspective, even though they're getting all the right answers, they still can't tell whether the prover is a perfect liar or an actual. So yeah, in terms of actual implementations, you're not going to be using a simulator unless you want to build one for like, I don't know, testing or experiments or something like that, or to do algorithmic proofs if you do like a computational proof helper or something like that. But this is all like just demonstrating the security of the system. And actually perfect zero knowledge, just like perfect secrecy, is usually too ideal of a constraint to go for a weaker conditional constraint. So I said like S was a Turing machine. Usually the security properties are proved with a weaker version of that simulator or adversary. All right, before we go into a more functional example of a zero knowledge proof, I want to do a sort of quick background review of vanilla Diffie-Hellman. So basic Diffie-Hellman key exchange over a multiplicative group of integers. Just to review, Diffie-Hellman key exchange is a way to basically do what's being asked in the purple text at the top of the slide. So there's a secure channel right? So anyone can eavesdrop in the communication channel, but Peggy and Victor want to exchange a secret that they both will know. So how can they do that over this unsecure channel? Because the secret that they want to end up with is the same. This is a form of symmetric key exchange. Once they have exchanged the keys, then they can use those keys to messages for secure communication between them. The numbers that we're going to be using are coming from what's called the multiplicative group of integers modulo n. If you remember, like block arithmetic, mod, those numbers with multiplication as the only operation. So we're not talking about addition. So that's what the x means next to the z. And because it's a group, so everything's got an inverse, right? So because of multiplication, there's nothing you can do for zeros. And another thing to point out, which is going to come up in general in a lot of these zero knowledge schemes, is the assumption of hardness. So this goes back to measuring like zero knowledge relative to some computational complexity, and why we were talking about knowledge versus information, right? So key exchange algorithm relies on what's called the discrete logarithm assumption. So the discrete logarithm assumption is basically a type of one-way function, or an assumed one-way function. So when you're dealing with integers modulo n, when you take any number to the power of another number, so like g to the power of x, that's pretty easy to compute. But if I say y is equal to g to the power of x, find x, so essentially what's log of y, or base g, that's actually really difficult to do in these groups of integers using multiplication. Because the inverse problem is harder, that's where you get these one-way or trapdoor functions. Now, these are proven to be one-way, so there's no complexity proof that the logarithm is always harder to find than the exponent or the power of a number in a cyclic group. But it hasn't been disproven. So basically, we're relying on this assumption. And this is another reason why you'd see people talking about post-quantum secure cryptography and things like that, because these problems are hard relative to certain computational models. If you have a stronger computational model, they become less hard. All right, so let's go through the actual algorithm here. Peggy and Victor first agree on a couple of parameters. So that's the base, and n, which is the modulus, and g, which is the base of the exponent. So if you're familiar with like clock, the modulus is 12, right? If it's now 11 o'clock and you add 2 hours to that, it's not 13. If you're using 12-hour clocks, it becomes the mod, which is 1. So they agree on that modulus, and then they fix some number in that group. So if it's z mod 12, they'll pick some number 1 through 11, and that's their agreed upon base. So after they agree on those two public values that anyone can read, then Peggy and Victor are each going to generate a secret value that only they know. So Peggy generates A and Victor generates B. Once they have those values, they're going to use those secret values and the two public values to compute an exponentiation, right? So Peggy will take her secret value, use that as an exponent, you do the A mod n, that becomes her public key or partial shared secret. Victor does the same thing with B, right? So he computes g to the power of B. Now Peggy's going to send Victor her public key, the partial shared secret, and Victor's going to do the same thing to Peggy, send over B. Now, just because of basic arithmetic, even though we're dealing with numbers from this finite field, right, the integers modulo n, same exponent rules apply, right? B is actually g to the power of B, so capital B to the power of A is the same thing as g to the power of A. And then same thing on Victor's end, he's got A, which is actually g to the power of A. He raises that to his secret value of B, and that's the same thing as g to the power of A times B. Just by using the partial secret public key they were each given and their individual secret values, they're able to compute a shared value, which is only known to them. Now, why is this possible? And that goes back to the discrete log assumption, right? So if finding the log, so if I gave you capital A and you could compute the log of capital A base G to find lowercase a really easily, then we don't have a one-way function. And this wouldn't work because given capital B and capital A, I can just take the logs and find lowercase a and lowercase b. And I can do the same thing as Peggy and Victor, right? So this entire encryption scheme crucially relies upon this hardness assumption, the existence of one-way functions, and that the discrete log problem is one of those one-way functions. Back to zero knowledge systems. The three properties that we want any zero knowledge system to have are the following: completeness. This is the kind of going in the affirmative direction, right? So if there's a statement that's true and both the verifier and the prover are honest, then if the system is complete, a prover will always be able to convince a verifier up to some arbitrary probability threshold. So no matter what threshold of probability an honest verifier who's actually not trying to be adversarial or do some algebraic voodoo, they would always meet that probability. Soundness is going in the other direction. So if the statement is false, then no cheating prover can ever convince an honest verifier about some small probability, right? Actually, the completeness thing is not probabilistic. Sorry, I made a mistake there. If you ever see one error, they're lying to you. That's on completeness. So completeness, you get 100%. The soundness is where the probability comes in, because if I'm like that Oracle simulator and I'm just a perfect liar, I could come up with some proof or something that passes your bar, your probability threshold, but it's as small as the probability threshold you set for sound. And the last property is zero knowledgeness, right? Which is, if a statement is true, then a verifier learns nothing other than this is true. And this paragraph here below that is basically trying to explain in words a little bit more what the mathematical definition of perfect zero knowledge is. So I do call it the simulator here. So whatever information a verifier learns is the same as if it were interacting with a simulator oracle, a perfect liar. The interaction history between the verifier and the prover is statistically indistinguishable from an interaction history between the verifier and a simulator that just correctly answered the challenges without knowing the secret knowledge or what's called the witness data or function. All right, so let's use the discrete log problem. Instead of using it for symmetric secret sharing, we'll use it for a zero knowledge proof. So now let's say instead of wanting to share a secret with Victor, Victor just wants to know that Peggy's public key actually corresponds to her secret that she hasn't shared with anyone. So this can happen if we have like an async setup. Rather than doing a handshake and then exchanging public keys and partial shared secrets synchronously, maybe Peggy has published her key information for anyone that wants to establish a symmetric secret in the future. But because it's asynchronous, there's going to be less trust in those public keys. So for instance, these public keys could just be on a publicly available database. So if anybody else has access to that database, they could just go grab Peggy's public key and say, hey, this is my public key, right? They wouldn't have the secret corresponding to Peggy's public key, but they could try to initiate some kind of communication just by grabbing some random key, maybe Peggy's, and trying to use that. So Victor, before he agrees to do the symmetric secret sharing with Peggy, wants to verify that Peggy actually controls the secret that corresponds to the public key that her name is tagged on. So here we're just using some specific number. She's got a secret number 2 in some modulus. We were talking about clock arithmetic 12. Really, to simplify things, you want it to be a prime number and you want it to be a large prime number. But yeah, that's more of a technical implementation detail. Here's Victor. He wants Peggy to prove that her secret number is less than 10, right? So this is a little bit different than before, right? This is where she doesn't have to prove the exact value. She just has to do what's called a range proof. So Victor gives her a range, and that's the challenge. She has to demonstrate that her value is in that range, and that's her response.
Could I ask a question because there seems to be an obvious way to hack this even without knowing how it works. And that's just, if you have an automated system for providing these proofs, and the number is like 32, has some range, can't you just ask for successively smaller ranges until you prove to yourself it's this exact number because it's not in this range, but is in this range? Like
yeah, so you could, but you would have to respond to this. And when we get to, I don't know if we'll have time, but if we get to succinct proofs versus non-succinct proofs and interactive versus non-interactive proofs, once you get to non-interactive succinct proofs, then basically you have batches of challenges that are generated. So basically you can check that challenges are in that specific format before you can generate the responses. You can even offload some of that challenge generation to the prover themselves through the use of cryptographic hash functions.
And one last thing, it might be good just to leave some time for questions, because I know there's some student questions and questions from the group.
Yeah, I'll just try to go through the zero knowledge version of the discrete log problem and then maybe take questions there. So we've still got the discrete log problem as before. So Peggy has some secret value S, and she also has the corresponding public key that she's computed, which is y equals g to the power of S, or mod p here. And just like before, Peggy and Victor agree on the generator, which you think is a base from before, and the modulus p. And Victor wants proof that Peggy knows S. Peggy does what's called a commitment, right? So it's important that Peggy does this generation and compute first, because otherwise she could essentially act like a simulator and cheat. So Peggy has a secret S corresponding to public key, and then Peggy commits to the value T. So she's going to fix some value V, maybe randomly or however, and then she's going to compute G to the power of V, and that's T, and then that's what she's going to send over to Victor. So B is another secret value that Peggy does not share with Victor, right? So it's essentially like another secret that's just randomly generated or on the fly generated. So we're calling that like the logarithm of the commitment, or the commitment log. All right. So Victor's just going to generate some challenge, right? Random number generator is probably good enough for this. And he's going to send that over to Peggy. Now, Peggy is going to compute a new exponent, R. And this equation looks funky. It's because it's basically an algebraic trick that's going to make sense in the next step. So Peggy computes that R and sends over to Victor, and then Victor is going to perform this computation. And again, because of Y being G to the power of X, right? Y is Peggy's public key and X is her secret. So they're related because Y equals G to the power of X. Raising that to the power C and raising G to the R, because the way that Peggy computed R is the same as G to the power of B minus X times C. So the XC terms are going to cancel out, and you're going to be left with G to the power of V. But that's exactly what the commitment value T is that Peggy had sent over earlier. So the only way that Peggy could have produced the correct value of R for Victor to use, the correspondingly correct value of T, is if she actually knew X and V, which are the secret. So X is the secret she's trying to prove, and V is like an ad hoc secret she's generated on the fly for this demonstration purposes.
And S is equal to X.
Sorry, X should be S there. So now, just as I said, these two T values are going to be equal if and only if Peggy knows S. But Victor's learned nothing at all about the value of S. And again, this is based off of the hardness assumption of the discrete log problem. So if discrete log is easily invertible, then in fact, Victor could just learn S and anybody could learn. Okay, previous protocol was interactive, right? So just like we were talking about before, these are probabilistic proofs. So you're going to have to perform this test several times until you hit your probability threshold. So what are some of the drawbacks of this protocol being interactive? One, it has to be synchronous, right? So Victor has to be there to receive the response. If you set some timeout or something, that could be an issue there. The other issue is just the time involved, right? Because it's interactive, there's network transport that has to occur every time the message is sent over. The latency in your system is mostly due to network, which it usually is. Your interactive version is going to be slow. If you could make it non-interactive, you could drop out all those network transmissions. So we can, in fact, make it non-interactive. And the way we do that is through the use of cryptographic hash functions. So rather than Victor having to be there to generate the challenges C sequentially and ad hoc, what we can do instead is, just like before, Peggy will generate a random value, but instead of, and she'll generate like the R and the T from that, but then instead of publishing that and waiting for Victor to just send out C, she'll use a cryptographic hash function to compute C from G, Y. So the inputs to the hash function Y and T, and outputs some value that is the challenge. And because of the properties of cryptographic hash functions, it's effectively the same thing as a randomness generated by Victor. So now instead of just publishing the commitment T or sending that to Victor, she publishes to some store, right? Could be a database, a ledger, whatever, the pair T and R. The cryptographic hash function that Peggy used is known. And because the modulus and the base are also known, G and P, and Peggy's public key is known, Y, you can use the hash function to compute C. And then any verifier like Victor can come along later, compute C, and just as before, run that same check and see that the T value computed from Y, T, G, and R is the same as the T value that Peggy had published. And when you get to something like Starks, you basically perform an aggregation of this where you have an array of values as opposed to a single. So instead of a single pair, you'd have two vectors of T's and R's. And with the single input multiple data architecture and stuff, you can do a lot of optimizations computationally. That goes back to some of the stuff I was talking about earlier, where depending on the encryption scheme, you can basically hit the limits of your numerical accuracy or your probability threshold.
Don, do you want to go to the example at the end just to save some time for questions, but also like tie things back in together?
If you were paying attention to some of Apple's press releases, I think last week they announced the Wallet ID program. They're testing in Arizona, and I think maybe a couple other states. So now in your Apple Wallet, you could have your driver's license. You can imagine things like, okay, you're going to a bar or you're going to buy a bottle of wine, and you need to prove that you're over 21. And so if you're using your physical license, if you think about what you're actually doing when you show your license, you're revealing all of the information on the license. Almost all the time, it's fine. You're not dealing with an adversarial cashier. But let's say you are, and they have photographic memory. Now you've just shown the cashier all of the fields on your license, right? So your name, your birthday, your address, right? If that's current, your license number, whatever else identifying information is there, right? When really all that you need to do was demonstrate that you're over 21, right? They don't need to see any of the fields on your license besides your birthday. And in fact, they don't need to see your exact birthday. All they need to know is that if you're in the US, that your birthday was on a date that was at least 21 years ago. So what you can do is a zero knowledge proof for what's called selective disclosure over your credential, being your driver's license, right? So you run a zero knowledge proof over your license, and it doesn't reveal any of the fields, but it produces a Boolean that says your age is at least 21 years ago. And then you can verify your age without sending over any of your personal information. So that's just a simple example. Once this technology is built, then all sorts of applications become, possible. And that's what we're working on at MEM.
That is really exciting to see the government actually using these. Apple and the government working together. That's so cool. Wow.
Yeah, I thought that last bit, seeing that application, is super interesting and exciting. Yeah. Do we have some time to throw some questions at you, Don?
Yeah, sure.
Cool. I've got a bunch accumulated in this thread in Discord right now. I'm just going to cherry pick a couple, starting with a simple question. How did you learn all of this ZK knowledge, and how should someone who's a newcomer best learn it? Is there like a crypto textbook that you could suggest to somebody that's a little bit more mathy than something like applied cryptography or something like that?
Yeah, it's definitely art field to stay up to date on, because there's just so much activity there. My background from school is in math, so I did a little bit of crypto, took some courses in school, and got my feet wet in the literature through that. But since then, it's mostly been finding resources online and going through the research and the textbooks myself. Matter Labs actually has a really good repo of resources called Awesome ZK. Let me post a link in the chat here to that. It's pretty exhaustive, and they go through several of the pretty widely used, at least in terms of what's being used, proof systems.
Anthony, can you get that to us?
Yeah, if it's difficult, I don't even know if we have the chat enabled in Zoom. So if you want to follow up on our email thread, I'll pump it out to everybody afterwards.
Yeah. Cool. And it's a pretty varied list in terms of skill level. So you'll find like intro, beginner, explain like I'm 5, all the way to like graduate level applied cryptographer.
It's called ZK Awesome.
Awesome. Actually, I've got it pulled up right now. The Matter Labs repo, look for awesome zero knowledge proofs.
I think we have time for one more question.
And I'd also recommend the textbook by Goldreich. It's a bit of a heavyweight, but
I'm going to give you one that's a little bit less technical, but a little bit more about Mem Protocol. So could you talk a little bit about Mem Protocol's bounty systems and Q&A communities? How do they improve on top of Stack Overflow or something similar to that?
The Q&A app is actually one of our earlier applications. We're more focused on the infrastructure stuff right now. So we started out basically with an application, and then we realized we needed some underlying infrastructure to actually deal with some of the issues with just the straight bounty system and how we would actually get something to be better than Stack Overflow. So the idea of a persistent reputation that isn't just pegged to one application. That leads to data interoperability and identity portability. So basically, I guess to answer the question, we're still figuring it out and we're focused on the infrastructure right now. Once we get that down, then we'll be able to deal with that with some other inputs.
Cool. All right. I'm looking at the clock and I know that you guys got to go. So I just want to give you a big thank you, Don and friends. Thanks for coming and sharing time with us. Thank you for sharing all this information with us. I know I could speak on behalf of all the students when I say this was really awesome and just thank you so much. I hope we get to see you again sometime.